Hello and welcome to this homework help video where we're going to talk about three problems that all have to do with electricity or the physics of electrodynamics. All right, so let's take a look at our three problems and let's go ahead and number them. 1, 2, and 3. They are each single part problems, so you can see they all each only have a part A. I have already customized the values so that they're a little different than you would see in an online homework system. But in such a system, if they're randomized, then who knows, they could match up by chance. So in the first problem, it is the most fundamental of the three because it covers Coulomb's law. And Coulomb's law is about as fundamental to electrostatics and the study of electricity as you can get. So I went ahead and pulled this image off of the internet right here. And let's put a box around it. We can think of this as our one key equation that we need to work with for problem 1. So we can practically think of this as a plug and chug problem because we just want to apply our values right into this equation in their appropriate variables. And we can see that the equation is going to give us a force, and as written, it's dependent on a constant called Coulomb's constant, also called the electrostatic constant, and you might hear me call it that. That's the more common name, I think, or the name I'm more used to, which has a numeric value, which is quite large, of 9.0. That's rounded to two significant figures. You also may see it as 8.99, and then times 10 to the 9. The units are going to be Newton square meters over square coulombs. And this is a unit that, a base unit that you would not see in mechanics where the units were meters and kilograms and seconds. So this is a new player to our now, alphabet of 4 base units. And this is the fundamental unit of charge. And, for example, an electron has charge. That charge is measured in coulombs. By the way, an electron does not have 1 coulomb of charge or anywhere close to that. It has a tiny, tiny fraction, 10 to the negative 16th of that. So the point is that we have a very small amount, or 10 to the negative 19th, excuse me, but a very small amount of charge per electron. Regardless, the coulomb is the amount, the numeric amount that's considered the base. Okay, just like a kilogram has a certain amount of mass, the coulomb has a certain amount of charge. All right, so there we have it. And I mentioned it's a large number because times 10 to the 9 is a billion. So we can think of this as 9 billion being the numeric value. Okay, and then the rest of the equation has up in the numerator the product of charges, so Q1 multiplied by Q2, and then divided by the distance between the charges squared. This relationship, this physical law, which being a law has been experimentally confirmed many times, is very similar in form to the universal law of gravitation, where we had the product of masses and the distance between the two masses squared. So both of those are considered inverse square laws. So there is more than one inverse square law, the universal law of gravitation, and now Coulomb's law are two examples of inverse square laws. So obviously there is some commonality here in physics, some truth that arches over both of these laws. Furthermore, it's worth noting that unlike the gravitational law, where we had a constant in front that was very small, now we have a constant in front that's very large. But they both are similar in that it's just some constant dependent on, not the particular situation, but just the universe we live in. So this constant never changes. Okay, it's constant. So now we're going to head and apply this key equation, but let's make sure we can interpret the problem and know where to put our variables. So we're told that 2 pellets, which are just some objects that hold charge in this case, so you think of that maybe as 2 spheres, are charged each with a charge of 3.3 microcoulombs, which when you see micro, what micro means is a millionth. So in scientific notation, that would be 3.3 times 10 to the negative 6, and then C for coulombs. The distance between these two charges is 1.4 millimeters, which converted to base units would be 1.4 times 10 to the negative 3 meters, because there's 1,000 meters in every, 1,000 millimeters in every meter. And if a picture is helpful, it would be pretty simple. It would simply be two spherical-like objects. So the first one was much more elliptical, obviously, and then they have the distance between them. So each of these would hold some charge, Q1 and Q2, and then the distance between them is R as written in the equation. Okay? And what are we asked to find? We're asked to find the electric force, which you may sometimes see labeled as the electrostatic force, but the name here is interchangeable: electric force, electrostatic force. All right? And that's going to be what comes directly out of Coulomb's law. All right? So let's go ahead and write the equation with the values and then plug it into our Desmos calculator over on the left. Okay? So we're going to be solving for a force. And as long as we keep everything in base units, the force we get will be in newtons. So we're going to put our value right here, our 8.0, because we're working with two significant figures, times 10 to the 9 newtons square meters over square coulombs, and then multiplied by the product of the charges. The charges need not be the same, and in this case they are, but they need not be. And so we would have 3.3 times 10 to the negative 6 coulombs. That would be for Q1. I'll go ahead and scroll over a bit so you can see the equation as I fill it in. And then 3.3 times 10 to the negative 6 coulombs for the identical charge, Q2. And even though the charges may be different, and although they're not in this case, the force will always be the same, thanks to Newton's third law, because they create a force pair, so there's no way for them to experience different forces. Also note that we're not given their masses. We don't need their masses in order to find the electrostatic force between them. If we wanted to know how much one of them accelerated, then we would need to know the mass, because we could use Newton's second law. But if we're not asked about the acceleration that would result from this force, if this force was the one and only net force, then we just simply don't need the mass. And let's go ahead and get our distance, that millimeter distance, down in the denominator, 1.4 times 10 to the negative 3, and make sure to square it. So as long as we plug everything in as written into our calculator, we're going to get our correct answer. All right, so let's go ahead and put over here our 8 times 10 to the 9th. All right, go ahead and close parentheses on not the exponent, but on the whole thing. All right, and then I'm gonna, over here, let's go ahead and open a fraction, and then we're gonna put our charge, the Q1, so 3.3 times 10 to the negative 6th. All right, and you know what? I'm just gonna go ahead and square that, because if you're multiplying two things by each other, that's the same as just one of them squared. So that, as written in the calculator, would be equivalent to what I wrote out by hand. So you can kind of see two forms of it. And then 1.4 times 10 to the negative 3. And then, as I mentioned, make sure to square that as well. And that's just because it's an inverse square law. All right. So there we have our answer. Yes, it's a large force, because this is actually a lot of charge. To have 3.3 microcoulombs would be a lot of charge to have in one place. That's a significant buildup of charge. And so we end up with a force, especially at this rather close distance of just a couple millimeters, or less than 2, of 44,000 newtons. And this definitely goes to show that electrostatic forces have the potential of being way stronger than gravitational forces, but unlike gravitational forces, they can cancel each other out because there's two types of charge. If you want more information about that, check out the videos that are focused on the conceptual side of it. But suffice to say that it's on the large scale, it's gravity that dominates the universe, not electrostatic forces. But on the small scale, you can get a lot of force out of electronics. All right, and electric forces. So let's go ahead and write this in. Get a slightly thicker pen, and we're going to write this in scientific notation. So it's 44,000, and if I write that in scientific notation, it'd be 4.4 times 10 to the 4, and then of course newtons. All right, so that's it for problem 1, which employed as our single key equation Coulomb's law. So let's move on to problem 2. Now in problem 2, we are told that we have essentially a lightning bolt because of a buildup of charge in the clouds. So let's take a look at what's going on and what's described in this word problem. So we're told that a charge, where it's given to us as a conditional statement, so but regardless, we're told that a charge of 8.4 coulombs flashes in a bolt from a cloud to Earth. And we want to know the change of potential energy of the charge. Okay? So we need to take the idea of the coulombs and our distance, as well as, not the distance, excuse me, as well as the voltage to get our answer. Okay? And key to actually being able to solve this problem is reading the first sentence, which I skipped over, so I apologize for that, because we have to start right here. So let me read this now. The potential difference between the cloud that I just mentioned, the storm cloud, and the ground is 100 million volts. Now, you probably heard about volts, right? You know, like batteries have volts, right? There's a certain amount of voltage that comes from a charge in the wall. So that's the volts that we're talking about right here. So let's go ahead and give ourselves a gray cloud that represents our storm cloud right over here. And so we're going to put our cloud. And what voltage is voltage is a difference. So it's like a potential, and it's not a potential energy, but it's a potential energy that has been divided by charge. We don't tend to do this with gravity, at least not at an introductory level. When we talk about potential energy, gravitational potential energy, we talk about it in joules. It has the form of gravitational acceleration times mass times height. So that's there are, mgh. Well, for electric potential, a lot of times we don't want to worry about how much actual potential energy there is, but instead just the how much, the basically the drop would be for any amount of charge. So we divide away the charge, which if we were doing that for gravity would be dividing away the mass. So essentially eliminating the dependence on mass in the case of gravity, in this case, eliminating the dependence on charge. So what this looks like as an equation is just this. So let's write this down as our key equation. And the reason that my explanation there relates directly to the idea of a key equation is because we want to be taking voltage and using that along with charge to solve for energy. So we want a way to relate voltage, charge, and energy. And what it looks like is sort of the definition of voltage, V, right? That's the variable we use. And that's going to be potential energy, so PE, and then which sometimes we also represent as U, by the way, if you recall that from previous videos, homework help videos, and then divided by Q. Okay, so that is our key equation, and I'm using PE to be consistent with the value or the notation here, right? So PE for potential energy, which also makes a little more sense than using uppercase U for potential energy, but there's pros and cons to both because there's only so many letters in our alphabet, and sometimes we have a lot of variables to represent. Okay, but again, this would be voltage right here. Okay, voltage is measured in volts. It's a rare case when both the variable and the unit have the same letter, in this case, both uppercase V. And this is potential energy measured in, as you may remember, joules, because all energy and work is measured in joules. All right, so potential energy right there, joules, and then we have our charge, right? Just like the charge that we're talking about in Coulomb's law, but now being applied to a different law. All right, so that would be measured in coulombs. All right, so I wrote it like this because I think this is the most kind of common way to express it, and it also is, as I mentioned, the definition of voltage, but we need to rearrange this because we are given V, so we're told that there is 100 million volt difference between the cloud, so this is our cloud up here, and this is our ground down below, and the 100 million volt difference we could represent as essentially what would look like a height between them, right? But it's a little bit more abstract than that. I'm not talking about the altitude of the cloud or something above the ground. So it doesn't represent space, but it does represent that there is a voltage difference between the cloud and the ground. And so that's right there. That is our 100 million volts. So 100 and a million, if you recall, is 10 to the 6, scientific notation again, and there would be our volts. Now, that's not proper scientific notation, by the way, because our decimal place is right there after the 100. So if we were to write this as proper scientific notation, it'd be 1.0, because the decimal place should always be after the first digit in proper scientific notation, times 10 to the 8 volts. That's 100 million volts. Okay? Just, 1/10 short of a billion, which is 10 to the 9th. Okay, and so that's our voltage difference right there. And because we also know how much charge there is, which is 8.4 coulombs, so essentially there's a bunch of, say electrons represented here as an E with a superscript of a negative sign, right? Because electrons are negatively charged, whereas protons, of course, are positively charged. So there's a bunch of electrons up here, way more than I could possibly draw. I mean, trillions upon trillions, trillions of trillions of trillions. And that total amount of charge comes up to a whopping 8.4 coulombs, which may not sound like a lot, but as I mentioned in passing a minute ago, a coulomb is actually a lot of charge. 1 coulomb is a huge amount of charge. 8.4 is a huge amount of charge. But of course, clouds and do build up a huge amount of charge, which is why they can release this, burst of energy as a lightning bolt. So the idea here was kind of fun to think about is we're thinking about kind of how much energy that lightning bolt has, and if you could harness that energy and charge up a battery with it, you have a lot of contained energy that could be usefully used, right? All right, so that's our picture, that's our equation. I mentioned rearranging it, so let's go ahead and do our algebra down here. All right, so this is going to be the algebra to rearrange our key equation so that we're solving for potential energy as asked for. And it simply comes down to getting potential energy by itself. You can see there's not much we need to do. We just simply need to multiply both sides by Q, because then that's going to cancel out Q on the right-hand side, leaving just potential energy by itself, and then leaving QV on the other side of the equal sign. All right, and I'll go ahead and, as I want to do, write the potential energy as we read from left to right, and then just QV. So that is just our rearranged key equation, and now we can plug in our values. Okay, so let's go ahead and write it out before. Oh, let's undo that unintentional movement there. Everything back where I want it. Yes, all right. So zooming back in, and we want to have our potential energy equal QV. So I'll put our Q value first, so 8.4 coulombs, and then multiplied by our voltage difference of, wasn't 8, it was 1 times 10 to the 8 volts. Okay, zoom out so you can kind of see everything together, and I'll enter it into the calculator. Okay, so we had finished our first calculation. I'm going to go ahead and drop down to our next one here. And so let's type in our values. 8.4, okay, times, it's weird not to have it, times 10 to anything, but on to the next one. Times, and actually, you know what? I'm going to stick with using parentheses that match the way I wrote it. All right, which I like to use. I think they make things easier to read and more clear, when we're separating our different quantities. Okay, so 1 times 10 to the 8, and that's it. Nothing squared. It is simply the product of voltage and charge to get energy. And we see then that we get energy of 8.4 times 10 to the, to the 8th, of course, right? Because it's 840 million. What are the units? Joules. So that's how much energy we would get if we could completely harness that built up charge in the cloud relative to the ground. Okay, so let's write in our answer. 8 point, in a way that's legible. I forgot that I made this even larger. I'm going to bring it back down to 0.6. So 8.4 times 10 to the 8 joules of potential energy. All right, so finally, let's go on to problem 3. Now, problem 3 is about more of the practical use of energy, because harnessing the energy of lightning bolts is not something we can really currently do with modern technology. Maybe something we can do in the future. But what we can definitely do is generate heat with something, in this case, like a electric dryer. All right. And I was thinking this is a hair dryer, but this is maybe more like a dryer for drying clothes. It's an electric dryer connected to a 120 volt source. So when you say that there is a certain voltage source, that's kind of like the cloud, right? Being a voltage source, because that the cloud had a huge amount of voltage relative to the ground. So same idea here. The plug in your wall has 120 volts relative to ground. Okay. Now that's actually what we call it. We call it ground. That's more of an abstract idea, but it represents just like, maybe, a piece of metal that's connected to the bedrock underneath you, right? So it literally ultimately becomes the ground, the huge mass of earth at some point. And, that's different than say being insulated from the ground. So if you connected that voltage to something else and had a big sheet of rubber between that, say metal object and the ground, then that would not be the ground because then the charge would not be able to physically move to the ground and move through a conductor because electrons are free to move through conductors. Other charges are free to move through, say liquids like ionic liquids and so on. But in this case, we're mostly, if we're thinking about electronics as we know them, we're thinking about metal wires and freely moving electrons. Again, check out the more of the conceptual videos that talk about what it means to have a current, because a current is just that, it's a flow of electrons. Okay, well, that's what's going on here, right? This is an electronic device, and we get 120 volts from the wall. Great, okay? That is our potential, right? Not our potential energy, just our potential, okay? More commonly called voltage. Now, what else do we have? We actually have a value of current, okay? Now, what is current? Well, current is coulombs per, coulombs per second. So it's a rate of flow of charge. So it's how much charge there is per second. So if I'm going to go ahead and write this right here, I had to pause and make sure I wasn't going to call it coulombs per meter because it's not a rate of distance. It's a rate of time. It's how much charge there is. So equation, all right, key equation as I like to call them, and it's going to be the definition of current. So current is represented as the uppercase letter I. Don't ask me why. And it's simply going to be the charge. So Q, I'm using an uppercase Q here. No big difference whether it's lowercase q or uppercase Q. And then that's going to be, although I've been pretty consistent about using lowercase, you know what? I'm going to switch back to do that. So lowercase q, and then so it's charge per second. So that is the definition of current. Okay, so if we have a second here, right? We have a rate of change in the sense that it's how much how much charge there is per time. We need to be given a value of time, and if you look down, the last thing that we are given is exactly that. We're told that this dryer runs for 5 minutes. So we got a standard, power outlet of 120 volts. We happen to know how much current that dryer draws, and we know for how long we run it. And what are we interested in? We're interested in the energy, okay? How much energy is used or released by that dryer, okay? So we're actually solving for the same thing in a sense that we did in the last problem because we solved for an energy there. In that case, we're just solving for the potential energy. Here, it's more like we're solving for the energy delivered, but it's still going to have units of joules, okay? So we need another equation though, because just having I, Q, and S isn't enough. So let's put a plural here because it's key equations. And the other equation that we need is an equation that's going to relate voltage, current, and, well, energy, all right? So the most direct way to do that is actually, and the way you would see it, is not one that goes straight to energy, but one that instead defines power, okay? But before I do that, I do want to label this real fast. I want to make sure to call this current, all right? And current has units of amps, and here is the charge, all right, which has units of coulombs, of course. All right, brain isn't working. And then we have our time, right? And you know what? I should have wrote T there because I'm mixing up variables and units because time is measured in seconds, and that's where I can put my S. All right, so it's Q over T because T for time, units is seconds, rather than Q over S. That's confusing. Okay, all right. So you may also be thinking, wait, we weren't given a charge. Well, we're not actually going to need it. So this is a key equation kind of only in concept only, I now realize, because although it's, I think, great to think about, what the definition of current is, we're not going to directly need this equation here. So let's actually get to equations that we are going to need, because those are the ones that I like to focus on in these homework help videos. So sorry for getting a little sidetracked there. But what we have, the equations we'll actually put used to, and again, this one's, very, very helpful conceptually, but not for directly solving the problem. Okay, so going down, the two equations we're going to need is power. So this would be the power from any circuit, or in this case, the power coming from the wall socket is just going to be the product of current and voltage. Okay, So this is called the power law, fundamental law, also very closely related to something called Ohm's law. Ohm's law relates voltage, current, and resistance. But here we don't have a resistance. There has to be some resistance because every dryer or heating element is based on the idea that there's just something that has resistance. Resistance just like is like a choke point for the charge and then turns that electrical potential energy into heat energy. That's what it's all about. And so that's what's going on here. But we were given the resistance, so we don't need it. So we're skipping over Ohm's law and going straight to the power law. Okay, so that would be the name of this equation. But more importantly, the variables are power. All right, now power has units of watts. Okay, which comes up in everyday language a lot. Things are measured in watts. Okay, and then we already talked about current right there, measured in amps. So A for amps, and then of course voltage in volts. Okay, but now I said that there would be, two key equations, and indeed there are, because how do we relate power to energy? Well, it turns out that power is just energy per time because the watt is a joule per second. It's just the rate of energy, the rate of energy delivered, the rate of energy used. That's what power is, right? For animals, right? It's like your metabolic, energy rate, right? By rate, I mean the energy per time, right? And here for electronics, it's all about relating that current and voltage per time. Okay? And so that means that we could then combine our two equations after I go ahead and label some of these variables here. I won't relabel power because it's exactly the same, but energy, I'm going to make sure to define. And we're not calling it potential energy because it's not, it's more like energy in motion, but it would have units of joules. And of course, then T is time measured in seconds. All right, and so both of these define power, and since they both define power, P and P, we can take these two equations, IV and E over T, and just set them equal to each other. So that would be our algebraic step, just to take the two equations and equate them. All right, so let's bring them together. So I'm showing here with arrows. So now our two key equations become one, and it's simply going to give us IV equals E over T. All right, so you can see how that happened by just setting P equal to P, which you're always allowed to do when you have two different laws that define the same variable. And then we want to solve for E because we are asked for the amount of heat generated, right? And remember, heat is a form of energy, as the variable implies. So then we want to simply multiply both sides by t because that will cancel out the t in the denominator on the right and leave us a t over here in the numerator on the left. And we'll rewrite it with reading from left to right with e, so, starting off, and it'll simply be I V. Well, I wasn't using a dot before, so I won't start now, but IVT. All right, so it's just the product of those three variables: current times voltage times time. That's all it is. Okay, and we'll want to do one conversion because we need to convert our 5 minutes into seconds. So convert to seconds because the minute is not the base unit of time. You can't leave it in minutes. You'll get the wrong answer. All right, so then finally, what is it going to look like before we plug it into the calculator? So it's simply going to be E equals, and the 120 volts, although I have current first, so I'll put the current first, so the 12 amps times the 120 volts times the 5 minutes, but converted to seconds. So that's 5 times 60, which would be 300 seconds. 300 seconds, just like so. All right, so now let's plug these all in. So 12, all right, times, and you don't have to do them on parentheses. You could definitely just put a multiplication symbol between each, but again, I think parentheses are easy to read. 120, and then times 300. There we go. That is the energy delivered in 5 minutes by this dryer. And it is, right, a substantial amount of energy, not nearly as much as a lightning bolt, but still, hundreds of thousands of joules of energy. And it would be with two significant figures, it would just be 4.3 because we'd have to round down the 2. And the 2 is not greater than 5, so it just would round down to exactly 4.3. And it'd be 4.3 times 10 to the 5 joules. 4.3 times 10 to the 5th joules. All right. So there is our homework help for these problems all about electricity. I hope this homework help video has been helpful. Thank you so much for watching.